In electrical closets containing a 208/120 volts bus-touch riser with a transformers, a ground bar is not typically necessary because the equipment grounding conductors within the distribution feeders adequately ground the busway, bus taps, distribution panel, and panel boards. However, when dealing with a 480/277 volts bus-duct riser and transformers located every 5 floors, a ground bar becomes necessary specifically on those floors where transformers are present. This ground bar facilitates the connection of the grounding electrode conductor, commonly referred to as the GEC. On floors without transformers, the GEC can instead be directly connected to the building steel, provided the steel is properly grounded and electrically continuous. Besides the grounding electrode conductor, several other items may need connection to the ground bar. These include equipment grounding conductors originating from various equipment located within the closet. Examples of such equipment include lighting fixtures and motors. Secondly, surge protectors also require grounding through the ground bar to protect against voltage spikes. Thirdly, grounding rods or plates may be necessary for supplemental grounding, especially in situations where soil conditions or other factors limit the effectiveness of the primary grounding system. Electrical closet ground bars are considered necessary in 2 primary scenarios. Firstly, when the closet houses transformers, making the connection of the GEC crucial. Secondly, when supplemental grounding is mandated, reinforcing the grounding system's integrity. In situations where neither transformers nor supplemental grounding is required, ground bars are typically not necessary. However, their implementation can still be considered a good design practice. Ground bars offer a convenient point for connecting grounding electrode conductors, streamlining the installation process. They also serve as a centralized location for grounding inspections and routine maintenance. Assessing the cost implications is essential when deciding whether to install ground bars. While the cost of ground bars themselves is generally low, it's imperative to weigh the costs against the benefits. In situations where ground bars are not essential for safety or code compliance, omitting them may represent a more economically sound decision. This consideration is critical in projects where budgetary constraints are a major factor. Grounding electrode conductor sizing generally follows the guidelines outlined in the National Electrical Code, specifically section 250.66. The size of the grounding electrode conductor is typically determined by the size of the service entrance conductors. For instance, if the service entrance conductors are 1100 kcmil copper, the grounding electrode conductor would need to be at least 3/0 American wire gauge copper or 250 kcmil aluminum. However, if connecting to a concrete encased electrode, the grounding electrode conductor only needs to be number 4 American wire gauge copper or number 2 American wire gauge aluminum. Equipment grounding conductors play a critical role in providing a safe path for fault current, helping to trip over current protection devices like circuit breakers or fuses. The equipment grounding conductor size is determined by the size of the overcurrent protection device protecting the circuit as per National Electrical Code section 250.122. For instance, if a circuit is protected by a 20 amp circuit breaker, the equipment grounding conductor must be at least number 12 American wire gauge copper. If the circuit is protected by a 60 amp circuit breaker, the equipment grounding conductor must be at least number 10 American wire gauge copper. Busways must be grounded to ensure electrical safety. According to the National Electrical Code, busways are required to be grounded per section 368.17. The grounding conductor must be sized according to section 250.122, based on the rating of the overcurrent protection device protecting the busway. Additionally, the busway's metal enclosure must be grounded, ensuring that any fault current can safely return to the source. Transformer grounding is essential for safety and proper operation. Transformers must be grounded according to National Electrical Code section 450.10. The grounding system typically involves connecting the transformer's neutral point to ground via a grounding electrode conductor and bonding the transformer enclosure to ground using an equipment grounding conductor. The size of the grounding electrode conductor is determined by section 250.66, while the equipment grounding conductor size is determined by section 250.122. These grounding connections ensure that fault currents can quickly and safely return to the source, minimizing the risk of electrical shock. Ground bars should be installed in a location that is accessible for inspection and maintenance. They should be mounted securely to prevent accidental contact or damage. It's also important to ensure that all connections to the ground bar are clean and tight to maintain a low resistance path to ground. The ground bar should be made of a conductive material, such as copper or aluminum, and should be sized appropriately for the anticipated fault current. Regular inspection and maintenance of the ground bar and its connections are essential to ensure continued grounding effectiveness. Surge protective devices, or SPDs, are critical for protecting electrical equipment from transient voltage surges. These surges can originate from various sources, including lightning strikes, utility switching operations, and internal equipment faults. SPD work by diverting the surge current to ground, thereby limiting the voltage across the protected equipment. SPD should be installed in accordance with National Electrical Code Section 285. SPD are typically connected to the electrical system at the service entrance, distribution panels, and individual equipment locations. The selection of an SPD depends on the voltage rating of the electrical system, the expected surge current, and the type of equipment being protected. Proper grounding of the SPD is essential for its effective operation. Grounding rods, also known as ground electrodes, are used to provide a low resistance connection to the earth. Grounding rods are typically made of copper or copper-clad steel and are driven into the ground. The National Electrical Code, specifically Section 250.52, outlines the requirements for grounding electrodes. The minimum length of a grounding rod is typically 8 feet, and the rod must be driven into the ground to a depth of at least 8 feet. In situations where it is not possible to drive the rod to this depth, it can be buried horizontally at a depth of at least 30 inches. The number and spacing of grounding rods depend on the soil resistivity and the desired grounding resistance. Typically, 2 or more grounding rods are used to achieve a low resistance ground. The resistance to ground should be verified using a ground resistance tester, and it should meet the requirements specified in the National Electrical Code. Building steel can be used as a grounding electrode if it meets certain requirements. The steel must be electrically continuous and in direct contact with the earth. National Electrical Code Section 250.52 ATWA allows the use of the metal frame of the building as a grounding electrode if it is effectively grounded. The steel structure must be connected to the grounding system using appropriate bonding techniques. It's important to verify the electrical continuity of the steel structure to ensure that it provides a reliable path to ground. The use of building steel as a grounding electrode can be a cost-effective and convenient option in many situations. Concrete encased electrodes, also known as UFA-grounds, are another type of grounding electrode that can be used. A concrete encased electrode consists of at least 20 feet of bare copper conductor encased in concrete. The concrete must be in direct contact with the earth. National Electrical Code Section 250.52 A3 outlines the requirements for concrete encased electrodes. The concrete encased electrode is typically installed during the construction of the building. It provides a very low resistance path to ground and is a highly effective grounding method. Supplemental grounding electrodes may be required in situations where the primary grounding electrode does not provide an adequate ground. This is often the case in areas with high soil resistivity or in situations where sensitive electronic equipment is being used. Supplemental grounding electrodes can be grounding rods, ground plates, or other types of grounding electrodes. The supplemental grounding electrode should be bonded to the primary grounding electrode to create a common grounding system. The use of supplemental grounding electrodes can improve the overall grounding performance and reduce the risk of electrical problems. Grounding system inspections are essential to ensure that the grounding system is functioning properly. Grounding system inspection should be performed on a regular basis, typically annually or biannually. The inspection should include a visual inspection of all grounding connections, a measurement of the grounding resistance, and a verification of the electrical continuity of the grounding system. Any problems identified during the inspection should be corrected promptly to maintain the integrity of the grounding system. Regular grounding system inspections can help prevent electrical problems and ensure the safety of people and equipment. Bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. Bonding is essential for electrical safety because it helps to ensure that fault currents can quickly and safely return to the source, tripping over current protection devices and minimizing the risk of electrical shock. Bonding should be performed in accordance with National Electrical Code Section 250. Bonding conductors should be sized appropriately for the anticipated fault current. Bonding connections should be clean and tight to maintain a low resistance path. Proper bonding is essential for the safe and reliable operation of electrical systems. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that current is leaking to ground. The GFCI will quickly trip the circuit, interrupting the flow of electricity and preventing electrical shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. GFCIs should be tested regularly to ensure that they are functioning properly. Arc fault circuit interrupters, or SIs, are devices that are designed to protect against electrical fires. SIs work by monitoring the electrical current for the characteristics of an arc fault. An arc fault is a dangerous electrical condition that can cause a fire. When an SI detects an arc fault, it will quickly trip the circuit, interrupting the flow of electricity and preventing a fire. SIs are required in many locations, including bedrooms and living rooms. SIs should be tested regularly to ensure that they are functioning properly. The National Electrical Code (NEC) is a set of standards for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years. Compliance with the NEC is essential for ensuring the safety of people and property. The NEC covers a wide range of topics including wiring methods, overcurrent protection, grounding, and bonding. The NEC is used by electrical inspectors, contractors, and engineers. Electrical permits are required for many types of electrical work. Electrical permits are issued by local governments and are designed to ensure that electrical work is performed safely and in accordance with the NEC. Before starting any electrical work, it's important to check with the local government to determine whether an electrical permit is required. Electrical inspections are performed by electrical inspectors to ensure that electrical work has been performed safely and in accordance with the NEC. Electrical inspections are typically required after electrical work has been completed and before the electrical system is energized. If the electrical inspection fails, the electrical work must be corrected before the electrical system can be energized. Qualified electrical personnel should perform electrical work. Electrical work can be dangerous and should only be performed by people who are properly trained and qualified. Qualified electrical personnel should have a thorough understanding of the NEC and should be familiar with safe electrical work practices. Hiring qualified electrical personnel is essential for ensuring the safety and reliability of electrical systems. Electrical safety is paramount. Always de-energize electrical circuits before working on them. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow safe electrical work practices. If you are not qualified to perform electrical work, hire a qualified electrician. Electrical safety can prevent electrical shock, fires, and other electrical hazards.